Today we're going to look at graphing polynomial functions, and today is June 2nd. Your note packet should have 4 pages, and again, you won't need a ruler. We're going to be sketching smooth curves. So let's start with a power function. If you have a power function, you're going to have this generic format, but what we see in the generic format is one of the terms is raised to a power, and in this case, it's the power p. You should also keep in mind that the value of a cannot be 0. If it does take the form of 0, it will wipe the function out completely, and you'll just have a horizontal line that says y equals 0. P has to take the form of a real number, but we know from our previous chapters that real numbers are positive and negative integers, they're decimals, they're fractions, so they really can take a variety of forms. So this is a power function. We're raised to the 5th power. What we can do, though, is we can combine several power functions to make what's called a polynomial function. And here's an example of a polynomial function. And you can see that we have 6 terms in this function. The graph of this is going to be very curvy. It will look like a roller coaster. Now, we always want to put our function in standard form. So we have the greatest power first, and then we're working our way down to the constant where there's technically, visually, it looks like there's no power. It's really x to the 0 power. And the greatest exponent will determine the degree of the function. Also, once you determine the degree of the function, we will have the same number of roots. So they're calling it degree n, but they're also saying it will have n roots. However, when you graph it, you may not see all n roots because some of them might be duplicates, and we call that multiplicity. So here's an example. This large function is a polynomial function of the 5th degree. The power of 5 is the largest. It should also have 5 roots, which means it's going to cross the x-axis 5 times when you graph it. This next example, its greatest power is 3. This is a 3rd degree polynomial. It should also have 3 roots when you graph it. So in this function, we can see it's a 3rd degree polynomial. It has 4 terms. Now, polynomial functions, we said, are going to be very curvy. They have lots of turns. They look like a roller coaster. The degree of the function will control the number of turns that the polynomial function has. So in this example, this is a 3rd degree polynomial. It doesn't match the function on the graph, but this is also a 3rd degree polynomial. Once you identify the degree of the function, and again, generically we're calling it degree n, it's going to have n minus 1 turning points. So in our graph here, this is a 3rd degree function. It has 1 less turn. So I should see 2 turns, 1 here and 1 down here. The same with this example that's not graphed. A 3rd degree polynomial should always have 1 less turn, so there are 2 turns. Sometimes we also discuss the end behavior of a graph, and it's going to describe the far left and the far right piece of the graph. This is where your arrows are located. So this arrow is one end behavior, and this arrow on the left is the other end behavior. The end behavior is determined by the highest power, and then also the coefficient on the highest power. Here's a little graph to help you with the end behavior of any graph. The first thing that you have to look at is your function an even function? which means its greatest exponent in it is an even number, 2, 4, 6, and so on. Or is it an odd function? So its greatest power is an odd number. This one happens to be 5. We've worked with cube functions, which has a power of 3, but it could be greater than that. So if it's even or odd, that's going to help determine it. Then we want to know, is that leading coefficient positive or is it negative? So if you have an even polynomial and the leading coefficient is positive, both of the ends are going to be pointing up. Think of a parabola. 2x squared, that's an even polynomial, and the coefficient is positive. Our polynomial or our quadratic would open up. You can also do the same if it's got a negative coefficient, like negative 2x squared. We know that the parabola would open down. So it's even, which means the end behaviors are going in the same direction, but the negative sign makes them point down. If it's an odd function, we always have one end behavior going up and one going down. If the coefficient is positive, this is the normal direction where the right-hand side is up and the left-hand side is down. But if it's negative, it flips over and the left side goes up and the right side goes down. You can always refer to the chart if you need additional guidance. If we look at our graph here, this is a polynomial function of a 5th degree. We should have 5 solutions. If you look, we've got 1, 2, 3, 4, 5. And we should have one less turn, so we should have 4 turns. Here's 1, 2, 3, and 4. In addition to that, we will also only have one y-intercept. So this is right here where it crosses the y-axis. If we were able to factor our polynomial function, we would come up with all the zeros or the solutions for this factored polynomial. Now, this is a little bit more difficult that we want to get to in Algebra 1. You'll learn how to factor these in Algebra 2. But when I graph it, I can still reveal the zeros because they're going to cross the x-axis. Now, this is a 4th degree polynomial, and I should see 4 roots, but I've only got 3 here. Remember, we said we could have multiplicity. If you look at the factored form, we have 2 identical roots of x plus 1, which means they're both at -1. So even though I only see 1, there's actually 2 there. So we do truly have 4 zeros. All right, let's look at example number 1. We have an even polynomial function. We should have 4 solutions. The end behavior then is also going to be determined by this -1 in front of x to the 4th. So let's start by graphing it. If you'll take a minute and put it into your iPad, it should look like mine. This is kind of a melted M. The end behavior, we said, was even. So both arrows should go in the same direction, but the -1 means they're both going to be pointing down. So both ends will be down. And my graph doesn't show the arrows, but you'll put those on your graphs tonight on your homework. The y-intercept, there should only be 1. I can see that clearly on the graph, but you might also want to look at your table, but this is at 0, -2. It's also up here in the function. This constant reveals where the y-intercept is. Now, the solutions. Since we're not able to factor a polynomial function like this yet, what I did is I graphed this, and I can see 2 of the solutions are clearly marked, one at -1, 0, and one at 1, 0. And those will pop up in the table from your iPad. The other 2 are not going to pop up, and I'm approximating them at -1.5 and 0, and then +1.5 and 0. I could technically be off, but since I haven't been able to factor this, I'm just going to approximate, and this is a good educated guess. The last thing we want to look at is the domain and range. Remember, the domain is the x-axis. As this graph expands and we see more values on both the x and y axis, you'll find that the domain is from -infinity to +infinity. So it's going to get wider horizontally. The range, though, is going to come from the bottom, so negative infinity, but we can only get as far as these two bumps. I'm going to approximate those because those points, again, do not show up in my table. So I'm going to say the range is from negative infinity to approximately about 1/3. I don't think it's quite 1/2, but they are inclusive, so I'm using the bracket. Let's do the same with example 2. If you want to take a second and add a graph and then type in your function, this is a 3rd degree polynomial. We should have 2 turns. But when you look at the graph, it only looks like there's one. Technically, there's a turn here and there's a turn here. It could also be that we have some multiplicity happening. Our end behavior, because it's an odd function, we have one end going up and one end going down. On the right-hand side, the end is going up. That's normal because our coefficient 2 is positive. We should have one y-intercept, and again, you can clearly see that on the graph, but it's revealed in the function itself at 0, 1. There is only one solution shown. Again, it could be multiplicity, but I'm going to approximate it at negative 0.6. You might approximate it at negative 0.75. That's a little bit more user-friendly. And we have graphed these in a previous lesson, so we know the domain is negative infinity to positive infinity, and so is the range. Tonight's homework is number 124. You're graphing polynomial functions. Make sure you follow the instructions and you put down all the information that's being asked. If you have any questions as you go through this assignment, please make sure you get in touch with me. Have a great day.